get started. So in last lecture, we started discussing ptrace and how ptrace mechanism can provide a way to intercept system calls. So let's take a step back and talk about what are the ways to do system call interception. So there are broadly two ways in which system call interception can be done. One of them is that, and when we say system call interception, what we are talking about really is, when a process makes a system call, you want to, intercept the call in order to perform a check on the system call itself and its arguments. Okay? And in addition, you may want to, depending upon what the functionality is, you may be interested in changing the system call arguments. Okay, so this is sort of what you want to do. And the question of user level versus kernel is basically where does the checker reside? Okay? So if the checker resides at the user space, then we call that as user level intersection. But if the checker resides in the kernel space, then we say it's a kernel intersection. Okay? So doing the checking in the kernel is, of course, has some advantages. For one thing, it can be more efficient because if you put the system call checker in the user space, then what happens is that each time a process makes a system call, then that system call has to be delivered to another process in user space. So that means you are, making a context switch from the kernel to the user just to deliver the system call and then to go back to processing the system call. So context switches are quite expensive because they involve things like flushing caches. Okay? And I have mentioned in the past that on today's processors, the biggest performance problem is because of the difference in the performance of memory versus CPUs. Right? So each time you have to get some data from memory, you end up having to stall the processor for hundreds of cycles, if not more. Right? And then if a process has to make several requests and each of them end up costing hundreds of cycles, then you have really slowed down the process. So this is what happens when the data that you want is not in the cache and you have to go to the memory, and therefore cache flushes and are quite expensive. Okay? And one type of cache is the TLB, right? So the TLB is a special type of cache which is used to do virtual memory lookups, right? So when you have to translate a virtual memory address to a physical memory address, you use the TLB, and because every address, every memory access requires this translation, so you ends up increasing the cost of cache flushes because you have to first worry about getting the address translation entries from the memory, and then using those address translation to do the translation, and then again get back to accessing the memory. So all of these factors mean that cache flushes are expensive, and as a result, what happens is that you want to avoid context switches in order to get better performance. Okay? So when you do the checking in the kernel, then the system call has been delivered into the kernel, and it's going to be processed in the kernel. So you just add, a few more instructions to check the system call, and so that is, you can get much more performance than having to ship that out to user level and then go back to the user kernel and resume the system call processing. But at the same time, programming in the kernel space is not easy, right? So it's an unforgiving environment, and there are, you're trying to make the system more secure, but if the checker has some bugs, then you are ending up introducing more security vulnerabilities inside the kernel. Right? So it is quite possible that you might end up making things less secure. So at the user level, then you have the cost of having to do the context switch, but then you have the advantage that the checker can be written in user space. So for instance, if GDB was implemented in the compiler, in the kernel, you can imagine that you would probably have a very unreliable operating system, because GDB is a fairly complex piece of code, and if it runs inside the kernel, it's probably not. It's probably going to crash your kernel much more often. Okay. Same way, if you're writing a checker that runs in the kernel, it may make the kernel much less reliable. Whereas here, if you run it in the user space, then the risk is much smaller. Right? So in particular, if let's say there's a process A that you are monitoring using another process B, then any errors in the checker will only affect that one process A, right? It's not going to affect the whole system, and that's sort of the advantage you get by working at the user level. Okay, so so this kind of interception can be done in two ways. One is called library interposition, which basically means that you run the checker within the same process as the one that you're trying to check. Okay, so you can immediately see that this is not a very secure arrangement, right? Because if the checking, if the process you're trying to check is malicious, then it can take a variety of measures to evade checking, and this is quite difficult to deal with, and it's a problem that we will talk about later on in this lecture and into the next lecture. Okay, so doing this, when the checking code and the checked code are in the same address space, making sure that the checker is secure is quite difficult. Okay. On the other hand, if you're not too worried about this problem that the checks could be subverted, then you have an advantage to doing library interposition, which is that again, there is no context switch of any kind, and so therefore it gives you the checks are quite efficient. Okay, and not only that, you also have the advantage that the data that you want to check is readily available, right? So whereas even when you work in the kernel space, let's say you want to check the name of a file, the file name is a string that resides in the process address space, and it's not in the kernel address space. So there is, it's not necessarily easy to get all the data that you need in order to do the check. Whereas if you're running within the same user process that's being checked, then all of the data is available for you to check, and therefore that makes it easier for you to do your check. So you have high performance, and you have the ability to sort of intercept higher level operations, not only system calls, but any library operation could be intercepted if you are basically intercepting library calls. Okay, so the problem, of course, is a security problem, and then you have the second approach, which is that the checker actually runs in a different process. Okay, so the ptrace method that we talked about is one where the checker simply runs in a different process, so you don't have some of these security problems that we just mentioned. So let's get back to discussing the ptrace based system call interception a little bit more. So, so in the last lecture we talked about how a process can attach itself to monitor the operations of another process, right? So we'll call that as a monitoring process, and then there is and both of them are running, talking to the kernel, right? So the monitored process, so before the system call interception can happen, right? So what the monitoring process does, so let's call this, process A, right? And this is process B. Right, so process A right, so and then it invokes a ptrace syscall operation, right? So remember that ptrace is system call. Its first argument is an operation, and the operation that it's going to invoke is the ptrace syscall. Okay, so the ptrace syscall is going to say what that process A is interested in intercepting the actions of process B. So now what happens is that the monitored process, makes a system call, right? And then the kernel intercepts this and delivers that to the monitoring process. Okay? So now the monitoring process can, I already explained in the last lecture that the ptrace interface allows this process to, the process A to examine the memory of process B or its registers and so on, right? And I also mentioned that the arguments to system calls are all in registers. So in order to understand what system call is being made, what this process needs to do is when the system call is delivered, right, it needs to look at the EAX register, which is the system call itself, and then registers like EBX, ECX, which contain the arguments to the system call. Okay, so process A can now look at all of that and determine exactly what system call is being made. So for some system calls like open, right? So what is being passed to the kernel is an address of a string, right? And the string is actually residing inside the address space of process B. So what A needs to do is to go and fetch those memory bytes, and then it will know, okay, this is exactly the system call. This is the file that is being accessed. Okay, and at that point, it can decide, whether it wants to allow the system call to go through, or it can also decide to kill the process, right? So if let's say process B is doing something unsafe and process A wants to terminate it, it can kill it. And the third option is that process A can modify some of the data relating to the system call, right? So it can change the arguments to the system call, or change the file that's being opened and things like that. And so that gives a fair bit of flexibility to sort of not only check but also alter the behavior of this process. And after all this is done, if this process says it's okay, so then the call goes back, and then the call gets executed in the kernel, and when it is finished, then the return code is again sent to the monitoring process, and then the monitoring process can say okay, and then the system call will return. Right? So you can see that it's not just one extra context switch. There are two extra context switches that are being made. Right? So normally, if there is no process that's monitoring, it goes inside the kernel, executes the system call, and comes back. Right? So now instead, it's going to the monitoring process once before the call is executed, and then once after the call is executed. Okay, so that's definitely causes some performance overhead, and that's to a large extent, the reason why all of this is there is because ptrace mechanism was intended for debugging, right? And then somebody decided, in addition to using it for setting breakpoints and so on, I'm also going to give you some system call tracing ability. Okay, and still the thinking is that it is going to be used for some kind of debugging or analysis that you would do on code that where maybe more in a debugging mode rather than production mode. And so there are all these overheads that exist. But the way things work is that once there is a mechanism in the operating system, then it was designed for one purpose, but people use it for other purposes as well. And so so there has been a lot of work that uses this interception feature to implement customized security checks and extensions and so on. And in your second programming assignment, you will actually explore some of these some of the things that you can do by doing this kind of system call interception. Okay. So to wrap up the discussion on this, let's think about one example of a security application that you can build. Right? So think of something very simple, like limiting a program from being able to perform any writing any files outside of, let's say, /tmp, right? Then the way that can be implemented is the monitoring process can look at all the open system calls, right? And it can check both the name of the file and the file permissions, okay? And it can check whether the if the file name is outside of /tmp, it can check whether the file permission is a write operation, and if that is the case, it can cause the system call to fail. Okay, one way to cause the system call to fail is, for instance, it can change the system call number to an invalid system call. right? Or it can simply change the file name to be an invalid file name, so it can provide a null pointer instead of the original pointer that was passed in. So there are many ways to change the behavior of the system call, and by using one of those mechanisms, that particular call can be made to fail. Okay? But don't forget that this race condition problem that we talked about, right? So it is possible that you know, there could be multiple threads running in this process, and one of those threads could be changing the memory that is being examined here, right? So if the file name is in memory, and this process is trying to examine that file name, there may be another thread here which is somehow changing that file name. Okay? Or you could have a collaborator process, right? And it is possible for the collaborator process and the monitor process to have shared memory, and the file name could be kept in the shared memory, and then process C might be trying to change it while process A is trying to look at it, right? So there can be a race condition because of that. This check could be subverted, right? So there are difficulties in using this mechanism to enforce all the security properties that you might want. On the other hand, it does give you a lot of flexibility because you're able to look at individual system calls and file names.